Okay, so this video is going to show you how to do the analysis part of this video experiment we started today. So I've opened up Logger Pro here. As I was showing you today, the first thing I've got to do is chuck a video in there, so I'm going to pinch Shabir's one. Okay, where it's gone first, desktop. Okay, there we go. Now the first step here is to open up your video analysis toolbar. That's this little thing here, 3 red dots and an arrow. Click on that. I'm going to pick the ruler because I want to set the scale. Remember, we trace along the length of this meter rule here, and let the computer know that's equal to 1 meter, and that'll set the scale for everything else. Okay, 1 meter. Yep, okay. Now I'm going to have to go through here and find one appropriate throw to use. So that'll be one where every frame has the ball in it somewhere. So Vu here threw a couple that went actually out of the shot, so we won't want to use those because we can't track it if it's out of the shot. So let's have a look. I'm just going to go through this, and that one will do. Alright. So if you want to rewind this, you have to actually stop it first by clicking that black square there. And I'm just going to go backwards, frame by frame by frame by frame. And there we go. Alright. So I'm going to start doing this frame by frame tracking from here. So remember, you press this here, the little red dot with the crosshairs on it. And remember, you're trying to aim for the middle of this. When it's moving fast, it will be a yellow blur. You just kind of aim for the middle of it. Obviously, it's not going to give you perfect results. When you go to write your prac report, this is going to be a source of error you might want to discuss. And remember, every time you click her, she goes forward by 1 frame. So keep doing that. Try and make it exactly in the center as best you can. It's not always easy. Maybe when you do it, you can take a little bit more time than I am. I'm just trying to make sure this video is not 15 minutes long. And that'll probably do. I might have one more frame. You can see here that because it's moving quite fast towards the end, you've got that blur. I've just kind of tried to aim in the middle of the blur. Okay, so that's that part done. I can actually now click out of there. And there's my little graph. Excuse me. So that graph is showing X position over time for the red dots and Y position over time for the blue dots. And you can see that the X position is actually kind of increasing. So in other words, it's moving to the left. It's moving to the right slightly as it moves up and down. So Vu's kind of chucked it in a slight arc there. I think he meant to chuck it straight up and straight down, but you can see it's actually kind of going to the right a little bit because the X distance is increasing ever so slightly. Anyway, that's not really what we want. For this purpose of this experiment, we're actually trying to work out acceleration due to gravity. And we're going to need to actually have a graph of the X velocity and the Y velocity instead. So in other words, how fast is it moving in the X direction, which will be the red dots, and how fast is it moving in the Y vertical direction, which will be the blue dots. So I got to change my graph. So I go over to here where it says X and Y. Not right click, sorry, left click. And I want to go down the bottom here to where it says more, and I want to tick off X and Y, and I want to tick on X velocity and Y velocity, then press OK. Alright, cool. Now we've got the graph of the Y velocity in blue there, and the X velocity in red. Now we can see two things from this. We can see that the X velocity basically hasn't changed. It's got the same value throughout. And that's kind of what we were aiming to show. We were aiming to show that the horizontal, or the X part of a moving object's velocity doesn't change because there's no force acting on it. The only part that changes is the vertical Y component of the velocity. And that's because there is a force acting on that. There's a force of gravity pulling that ball back down to the ground and causing it to accelerate. But remember, the force of gravity only acts in a perfectly vertical, straight up, straight down direction. So the force of gravity is not going to make the ball speed up in the x direction. It's going to maintain a constant speed. You can see here that that's constant speed is a little bit more than 0, because as we saw on that last graph, it was moving ever so slightly to the right. But it's not so much about the actual value of the x velocity. It's just the fact that if you look at that, it hasn't really changed. There's a bit of scatter there, but if we add the line of best fit to that, it would be pretty much perfectly flat, which means no change. Whereas this guy here, you can see, is going down. So it starts going in the upwards direction at about, what would that be, 1.8 meters per second. But you can see that its upwards velocity decreases until it reaches 0 here, which would be the apogee. And then it starts to become negative, which is when the ball is starting to head downwards. Now, basically what we've got here is a velocity time graph. And you'll remember from kinematics last term that the slope of a velocity time graph is equal to its acceleration. So in other words, if we find the slope of this graph, we should find that it's equal to acceleration due to gravity, because that's what's acting on the ball as it falls. So we should find the slope of this graph is negative 9.8. That's what we're trying to do. Okay, now the first thing we've got to do here is basically work out, well, we'll put this into Excel first. So we're going to put all of this data into Excel and make another graph in Excel. The reason I'm doing that is because I find that the actual graphing and adding a line of best fit process is easier in Excel than it is in Logger Pro. And once we've actually got this data into Excel, we've drawn a graph, then we're actually going to be very selective about which parts of this data we use and which parts we don't. But anyway, let's get this stuff into Excel first. So I'm just going to click here where you've got your raw table of values. And this is what our table looks like. We've got the time here, that's a horizontal axis quantity. We've got x distances and y distances, and an x velocity and y velocity. Now, we don't want the x and y distances. We just want this x velocity and this y velocity, because that's what we're trying to do. We're trying to do a velocity time graph. So I really don't want to copy these into Excel, so I might just do this. I'm going to click on this, hold down the left mouse button and drag it over to here. And then the same thing for the y velocity. So the first 3 columns are now the 3 we want. And once I've done that, I actually click in this first cell and I drag and I highlight all the stuff I want. Once I've clicked and dragged, I let go, click the right mouse button, press copy. Now I want to go to Excel and click in an empty cell, right click and go paste. And there you go. It looks a bit messy the way it's formatted it, but that's what we want. So let's just actually label these columns. The first one was the time in seconds. The second one, let's just double check to make sure I don't stuff up. Yep, second one was x velocity. So I'm going to put x vel here for velocity. And in brackets here, I'm going to just note that it's in meters per second. And then I might actually just copy that, paste it into the next cell. And this is the y velocity, so I'm going to change that x to a y. Maybe not. There we go, beautiful. And now we should be actually ready to draw a graph. So I'm going to highlight all of that. Going to go up to insert, going to go for a scatter graph. Beautiful. So there we go. We've pretty much got a carbon copy now of what we had before. The only thing I probably want to do here now I've got this graph, I'm not going to go through the process of like adding axes, labels and all that kind of stuff, because you should know how to do that by now. That's just going to waste time. One thing I want to do here is I want to get rid of this first part. You can see that it's not really straight here. It kind of curves down. And we're looking for a straight line. This isn't perfectly straight because you've got a bit of scatter in your results. A lot of that probably had to do with the fact that it was hard to judge where the center of the ball was when you clicked on it. But this is more or less a straight line where it's quite clearly not here. And that's because these parts was where I wasn't quite sure whether the ball was actually still in Vu's hand and being accelerated as he moved his hand upwards, or if it actually got to the point where he'd let go of it. It's very hard to tell because you see the hand follows the ball up as you throw it. And even after you've just let go of it, the hand still kind of follows up, so it's hard to see exactly when you've actually let go. Once you've let go, you're not accelerating the ball anymore because you're not putting force on it. That's when the gravity starts kicking in, and that's when you've only got one force acting on it, and that's when you get your straight line like that. So I probably want to maybe chuck these first 4 points, and then I'll just work with this part here because I know it was in free fall then. So I'm going to go up to here. I'm going to highlight the first 4. Oops. Highlight the first 4 and try deleting that. See what happens. Look at that. Sweet. Beautiful. So I want now to add a line of best fit to each of these. I'm going to add a line of best fit to this, and hopefully it should be like more or less 0, because we're expecting no change in that. And when you have no change in something, that's a flat horizontal graph. So line of best fit, yep. I'm going to display my equation on the chart. And let's move that over slightly across. And look at that. That's pretty much perfectly flat. Okay, remember when you have an equation of straight line, it's y equals mx plus c, where m is the slope. Now in this case, the slope is 0.0065. That's pretty bloody close to 0. So we've basically shown here that for that particular throw, horizontal velocity doesn't change at all. If you want to know what the actual horizontal velocity was, that's that second number here, 0.1322. So the ball was moving to the right at 0.1322 meters per second as it was thrown, which is basically bugger all. Okay, next one. Take this one here, the y velocity one, add a trend line. Whoops. Add a trend line to that. Again, we want a linear one, and again, we want to display the equation on the chart. And pow, there we go. Now, this is your magic number here. Again, it's y equals mx plus c, and so this number here in front of the x is your slope. And remember we said, because this is a velocity time graph, the slope of a velocity time graph is acceleration. So this number here is the acceleration that's acting on that object as it falls. So in this case, negative 9.673 meters per second squared. And that's pretty bloody close to what we expect to get, which is 9.8. Now there could be a number of reasons for that. It may be that it's just a bit of random error caused by the fact that it was hard for me to judge exactly where to click on in each bit. Or it could be that we're seeing what we call the net acceleration. So we've said that the only force acting on it as it falls is gravity, and that force makes it accelerate at negative 9.8. Well, we know from what we've talked about in class that's not strictly true. There will be some air resistance acting on that ball as it falls. Now, I'm pretty sure Vu and Shibuya used a golf ball, so the air resistance won't be too much on it. But even so, that air resistance provides a force upwards which takes away from the original downwards force of gravity. So you'd have slightly less force than you would if you were in an airless environment, which would mean slightly less acceleration. So maybe that's why we've got negative 9.67 instead of negative 9.8. Don't know. Anyway, so that's how you basically do it. And you probably want to do that for 3 or 4 different throws. And then maybe at the end you just average those slope values. So you take the slope for this one, which is your acceleration for this particular throw, and then do the same thing for the next throw in your video, and then the same thing for the next one after that, and the next one after that, and then average it. And that will be your average final answer for this experiment. Alright? Make sure you have a look at this. Actually, that's a stupid statement. If you got to this point, you have already had a look at it. Oh my god. Anyway, I hope this has made things a little bit clearer. It's a bit fiddly at first, but if you have a play of it, you should get pretty quick of it. And it's a hell of a lot faster than doing it the old-fashioned way with ticker tapes and stop-motion photographs and stuff like that. So, hope this has been helpful. All the best. Ciao for now.